So theorem 7 says an n by n matrix A is invertible if and only if A is row equivalent to the identity matrix. And in this case, any sequence of elementary row operations that reduces A to AN also transforms AN into A inverse. And so what this is saying, we talked about this yesterday, is saying that if you start with A augmented with I and you row reduce, you do your RREF, then you end up with I augmented with A inverse. And so this gives us our algorithm for finding A inverse. Find A inverse, we row reduce the augmented matrix AI right here. And if A is row equivalent to I, so if the A part right here turns into the I part there, then you know that the matrix is invertible. And furthermore, you know that the thing over here is the A inverse. If it doesn't work, then A does not have an inverse. Let's do another example here. Again, bust out your techs and friends for me. I say do it by hand, but I think we'll just do it using technology again. You're gonna enter not a 3x3 matrix, but a 3x6 matrix. Augmented with the identity matrix. The A is going here, and then we're augmenting with the identity matrix on the left. We row reduce. You could use your text and friend for this. So we row reduce, and I've got, how about we'll do it this way. You get star, 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 and then what kind of stuff do you get over on this side? You get a whole bunch of weird numbers, right? Do you get a 0? Should get a 0 here. And then you get a whole bunch of stars over there, right? What I want to point out is that we have this 0, 0, 0 here. Phrased another way, you don't have the identity matrix. So it's not the identity matrix. So what do we conclude from all this? Yeah, from such a no inverse. So we'd say A is not invertible. Or you might say that A is singular. So one more calculator tip here. We have found the inverse by doing row reduction. You can also find the inverse by using the reciprocal button on the calculator. Be like x to the -1. And here you would just enter A as the 3x3 matrix, and it would tell you that there's no inverse. I'm not a big fan of this particular button, so you can use it all you want, but if you're turning in work to me, then I want you to show me the row reduction step. So for the assessments, I want you to use RREF to find inverses. Makes sense process-wise. So here's the first method we taught. Here's another method that you can use to do the same thing. And what I'm saying is for the assessments, I want you to use this first method.
It's gonna give us the same answer, right?
It'll give you the same answer. So if you're doing your homework, using that second version can save you a little bit of time. And I have no qualms about you doing it to save yourself a little bit of time. But I want you to use the RREF because it reminds you of what's happening and what's going on. It's not just a magic button. All right, let's begin talking about characteristics of invertible matrices as outlined in section 2.3. So we're talking about characteristics of invertible matrices, and we have a list here of K equivalent statements. So it says let A be a square n by n matrix, then the following statements are equivalent. That is, for a given A, the statements are either all true or all false. So A is invertible. A is row equivalent to the identity matrix. A has n pivot positions. The equation AX equals 0 has only the trivial solution. Columns of A form a linearly independent set. Linear transformation X to AX is 1-to-1. The equation AX equals B has at least one solution for each B in Rn. The columns of A span Rn. The linear transformation X to AX maps Rn onto Rn. Then there is an n by n matrix C such that CA equals I. There is an n by n matrix D such that AD equals I. A transpose is an invertible matrix. These are all equivalent. This next theorem 5 from 2.2 could also make G, and again, G is this idea here. We could kind of combine these to say that AX equals B has a unique solution. Hope that helps. So it's just kind of another way of phrasing the same thing there. This next little claim, if A and B are square matrices and AB equals I, then by J and K, both A and B are invertible with B equals A inverse and A equal to B inverse. It has a little proof, and I'm going to leave that proof in the notes or in the text, or if Felix or Kyle wants to do a video on it, or somebody else wants to join the honors videos project, maybe we can get a classmate to walk through that particular little proof. But again, the notes are online for that. So I want to focus in a little bit on what this invertible matrix theorem does in dividing matrices into two types. There's two types of matrices in the world. There's the invertible ones, and there's the not invertible one. There's the singular matrices. Singular, I can't spell. So it's singular on one side, and then what is it on the other side? It's non-singular. Good. You could have n pivot positions, or you could have less than n pivots. You could have that the columns are linearly dependent, or the columns could be linearly independent. We could say that AX equals 0 has only what kind of solutions? The trivial solution. Or you could say that if it's non-invertible, then that would mean that AX equals 0 has non-trivial solutions. Again, these are sort of like equivalent statements. I got to keep going. I need more space, so I'm just going to move over. Invertible and non-invertible. Let's see. We have that the linear transformation is onto Rn, and then you'd have that it's not onto. The columns of A span Rn. A transpose is not invertible versus A transpose is invertible. So AX equals B always has a solution. Or it has no solution for some B. There's a lot of equivalent statements here. You could have the linear transformation is not one-to-one, or the linear transformation is one-to-one. And I think the last one on my list is that A is rho equivalent to I. So A is rho equivalent to I. You can rho reduce to I, versus A is not rho equivalent to I. Crazy. It's a lot of statements. Again, it's sort of like that Arc of Triomphe, where if you have any statement on the left side being true, then all the statements on the left side are true. If any of the statements on the right side are true, then all the statements on the right side are true. And you can see that each one of those statements is perfectly matched. Okay. Questions? Nice part about this class with the presentations, you don't have to memorize this, but you will need to know it and you will need to use it. So I guess I would suggest that you be ready to talk about these things when the time comes to present on 2.3. So it's something that would make for good questions. Like maybe you have something about an invertible matrix, and I'd be like, hey, why don't you tell me a few other things that would be equivalent to saying it's invertible? And I might ask something like that as a follow-up question. So it's not meant to be a trick. You don't have to go and memorize it, but this is something that you should have ready to go because it's a big deal. So if we want to figure out whether matrices are invertible, maybe on the left side, we could row reduce, and we could say, we could REF A. And if we REF A, we're going to get 1, 0, 0, 0, 1, 0, 0, 0, 1. You see that A, and notice that it has 1, 2, 3 pivots. So since it has 3 pivots, what does that tell you about A? So thank you. I can't see everybody. Thank you, Gerald, Felix, Twee, Tommy, Ratana, Sammy. It is invertible. So A is invertible. So maybe we could take our B and we could row reduce. And when you row reduce, you end up with something like ooh, sorry, let me change my notation here. It should be the tilde mark, right? Because it's row equivalent. So when I row reduce B, I'm going to get 1, 0, negative 2, negative 2, and I've got 0, 1, 2, 0, 0, 0. And what I want to point out here is that there's only 2 linearly independent columns. There's only 2 linearly independent columns in B. Those would be these 2. Okay. So since you only have 2 linearly independent columns, that must tell you that it's not invertible, right? B is a singular matrix. It's not invertible. Thank you. Be careful. This invertible matrix theorem only applies to what type of matrices? To square matrices. That's right. And sometimes you'll see the word square, but as Alex said, other times instead of saying square, we'll say n by n, or maybe we'd say m by m, something where you have the same number of rows and columns. Okay. Actually, that's really funny. Do you notice that I just circled the word square? That's kind of funny. So we should fix that. There. We squared the word square. Okay. Keep going. So if A is invertible, we can also think about the idea of invertible matrices, or specifically A inverse AX linear transformations in light of linear transformations. And so what A inverse times AX represents is it's saying you start at X right here. And then next you're going to find AX. Okay. And so that would be to this, your AX right there. And then after that, your end would be to find I guess A inverse times AX. So A inverse is going to take me the other direction, and I'm going to end up right back where I started. So we get that A inverse AX is equal to X. Nice, Elijah. I too am a square sometimes. All right. So one thing to note about this that's a little bit odd is that if you have, like, imagine that you had A, B, C, D times X. Okay, you would do transformation D first, then C second, B third, and A fourth. So we're doing our transformations from right to left, not from left to right. Okay. One reason is there was that question that I asked at the end of class the other day about how many multiplies does it take, and you told me that it takes a lot less multiplications to do matrix times vector and then matrix times the resulting vector than to multiply the matrices together first. And so it's more efficient to run this direction. Questions? Let me talk a little bit about this picture right here, because this picture, we're going to see a lot of pictures of this type as the course progresses. So let me apply that idea to this ABCD illustration. So what this would be like saying is you start with X, and then you're going to go to DX following transformation D. So I go from X to DX, and then I take transformation C to C times BX or CBX. Sorry, CD, I can't read my own writing. CDX. Okay. And then you follow that along B. This one is a B. And you get B, C, D, X. And then in this case, you end by doing A last, and you get A, B, C, D, X, something like that. So these fellas here, these are all linear transformations. Okay. Drat, come on. Those are your transformation matrices, and you run them from X to the DX to the CDX to the BCDX to the ABCDX, something like that. Keep going. All right. In general, if a linear transformation T from Rn to Rn is invertible, sorry, let me get my grammar right. A linear transformation t from Rn to Rn is invertible if there exists a function s also from Rn to Rn such that s of t of x equals x for all x in Rn and t of s of x equals x for all x in Rn. So this might look weird, but you might remember formulas from your past, like things like e to the ln of x equals x, because those were inverse functions, or ln of e to the x equals x. Or you had sine inverse of sine x equals x, things like that. And so this statement up here is just a general case talking about inverse functions. And notice one difference is that in this case, it works for all x's, whereas in some of the cases we've had to worry about in the past, you had to worry about restrictions on your x's. And same thing, there's going to be some issues here with the x's in your inverse trig functions. So in this case, we call S the inverse of T. And write it as T inverse. So theorem 9 says, let T go from Rn to Rn, be a linear transformation, and let A be a standard matrix for T. And T is invertible if and only if A is an invertible matrix. In that case, the linear transformation S given by S of x equal to A inverse x is the unique function satisfying equations 1 and 2. This 1 and 2 here is a reference to 1 and 2 up here. Let me see if I can write this in this theorem 9 in a more helpful form. So if it's a linear transformation, then you have T of x equals AX. And T inverse of x is equal to A inverse of x. That's what it's basically saying. Okay. So let's go back to these equivalent statements for a moment. So what can be said about a one-to-one linear transformation T going from Rn to Rn? So we have that T is one-to-one. Okay. And so what can you tell me about the columns? So maybe I should say where T of x equals AX. So what can you tell me about the columns of matrix A? So they would have, all those columns would have a pivot. Yep. Yep. The A is invertible. Yep. So I've got okay. But I think that what I'm actually after is, I think I want to go back to section 1.9. If I go all the way back to 1.9, and I think it's 12, where's this? Right here. It's been a while, but in 12 it says, oh, that did not work. Sorry. So if T is 1 to 1, if and only if the columns of A are linearly independent. The columns of A are linearly independent. So the columns of A are linearly independent. That's what we were talking about there. So if the columns of A are linearly independent, then we should be able to go back to our equivalent statement. Let's see, here's that. Columns of A form a linearly independent set. That lets us jump to the idea that A is an invertible matrix. So we went from T 1 to 1 to here, and then we can jump up to A being an invertible matrix, which allows us.
So how do I know, Bro, I didn't trust Sean,
Okay. Which allows us to say that if A is in, since we know that A is invertible, that must mean that A inverse is the inverse to T inverse. So this tells us that T is invertible. Invertible. T is this. Okay. So just kind of using that arc of triumph concept where we start with T is 1 to 1, we go to a theorem, it tells me the columns are linearly independent, then we go to another theorem that says that's equivalent to A being invertible, we go to another theorem that says that means that T is invertible. So we started with T is 1 to 1, and we just have that that's equivalent to T being invertible.